Alright, so today we're going to start looking at Chapter 8, which we call Chemical Equations or Reactions. So before you took this class, if someone had asked you, when you think of chemistry, what do you think of? You likely would have answered, you mix some stuff together and make some new stuff. People always envision the lab experiments they see on TV where you have two brightly colored solutions and you mix them together, and with a puff of smoke it changes into a new color. So we're not exactly going to do that, but we are going to get into what most people would consider, true chemistry, the chemical reactions. So before we start looking at chemical reactions, we need to make sure we're all on the same page with our background material that you probably learned in 8th grade physical science. And then we'll learn a couple of more symbols, and we'll review our naming. And then in the next couple of videos, we will jump into looking at the different types of chemical reactions. So we already looked at one type of chemical reaction earlier in the year. We looked at some nuclear reactions. So if you remember, nuclear reactions were when some type of change occurred with the nucleus of an atom, and it typically converted one type of atom into an atom of a different element. Okay? So it completely changed the identity of the atom. So none of that will be happening here. We're going to look at the far more common types of reactions that we'll deal with in the majority of chemistry. So a chemical reaction we define as a process by which one or more substances are changed into one or more different substances, okay, with new chemical or physical properties. So that doesn't mean, as I said, that we're changing, one atom into a different type of atom. That means we're changing the combination of atoms that we have to make molecules, okay? So we might have something like hydrogen and oxygen combined to make water, okay? So we're either combining atoms to make molecules, we're breaking down molecules to make single atoms, or we're rearranging the atoms of molecules to make new molecules there. So we know we represent this concept of reactions with chemical equations. Okay? So a couple of things about a chemical equation when we write them out. We typically write chemical equations with symbols. We can write them out in words though. We know that the arrow shows us that a reaction happens or a transformation happens. So we know anything on the left side of the arrow is a reactant, anything on the right side of the arrow is a product. Okay? We know that when we have chemical reactions or chemical equations, we always want to be sure and balance the equation before we finish. Okay? Because the law of conservation of mass tells us that we cannot create or destroy anything in the reaction. We simply rearrange the atoms. Okay, so if we have 3 carbon atoms on the reactant side, we also need to have 3 carbon atoms on the product side. So you'll see that will be our responsibility to ensure every time that a reaction is balanced. So we balance reactions with what we call coefficients. Okay, so if I had a simple reaction, we'll just say A2B, so I use the generic symbols A and B, and we'll say A2B breaks apart and it turns into A plus B. Okay? The only thing that I'm allowed to do to balance this reaction is add coefficients. Okay, so I'll put lines where I could put coefficients. Okay? So all I'm allowed to do at this point, once I have the reaction written out, is to put numbers in the blanks. Okay, that is the only change I can make, and this is where the large coefficients go. So in order to balance this, I put a 2 right here. I can go back and double check myself. There are 2 A's in the reactants. There are 2 A's in the products. There is 1 B in the reactant. There is 1 B as a product. Okay, so we're good there. I can also write in 1s there. It's not necessary. The 1s are understood. It's okay to write it in. One thing that is definitely not okay would be to add a subscript there. Okay, so we never use subscripts to balance equations. We only put coefficients out in front of reactants or products to make sure that the equation is balanced. So you'll notice in the the example that's typed out in your notes, one of the products is energy. Okay, so that's kind of a strange concept, and we'll spend a great deal of time discussing energy as a product or reactant in the spring, but for now, let's just talk about the basics of what that means. So if we have energy as a product, that means during the course of the chemical reaction that energy is released. Okay, so we don't create energy. we're converting energy from one form to another that we observe. Okay, typically we're converting chemical energy to thermal energy that we can observe as a temperature change. Okay? So if energy is released during a reaction, so energy is written as a product, we call that an exothermic reaction or an exothermic equation. So we can write that in a couple of ways. We can write it as it's written in your notes, plus energy, or we could write it as this. So I'll just look at the reaction I already have written. I could write plus 12 kilojoules per mole. Okay? So if I write that as plus 12 kilojoules per mole, I remember that joule is a unit of energy. So that is saying for every mole of reactant we have here, I will produce 12 kilojoules of energy. So then the opposite could also be true. It could also be necessary that I have energy on the reactant side of the equation. Okay, so that means that energy is used in the reaction. So typically we think about that as thermal energy being converted into chemical energy. So we will see a temperature decrease with the reaction. So that would just be the exact opposite. We would write energy as a reactant for an endothermic reaction. So an endothermic reaction we think about as absorbing energy. So we'll come back to that and discuss that in great detail in the spring. For now, just be aware of those two terms and know that for now we don't need to balance that energy when we see it in the equation. So we only need to balance the atoms. Okay, so if you see plus energy as a reactant or a product, there's no need to try and balance that in any way for now. Okay? So before we jump into the types of reactions, we need to think about how we know when a reaction happens. So that might be kind of a dumb sounding question, but just because you mix two chemicals together, just because you put two molecules beside each other, doesn't mean they're going to react. Okay, so not all molecules, when combined, will undergo a chemical reaction. So there are several ways that we can detect if a chemical reaction actually occurred, but there are three major ones that we'll see in this course and we'll see in lab. So the first way that we can detect a chemical reaction has occurred is a color change. Okay. So if you mix together two clear liquids and they turn bright blue, you can probably guess some type of chemical reaction occurred there. Okay. The second way we detect a chemical reaction is a temperature change. Okay. So if you mix two things together and they heat up or cool down, you can guess some type of chemical reaction occurred there. And the third is the change in state of matter. So we have to kind of be careful with this term or definition. Just because we see a change in state of matter doesn't mean a chemical reaction occurred. So if we have ice and we take it out of the freezer and put it on the counter, so frozen water, it will change states of matter. Okay, that's not the result of a chemical reaction. It's simply a physical change. What I mean by change in state of matter is you mix two liquids together and they start bubbling. Okay, so if you see bubbling, that means a gas was formed. Or if you mix two liquids together and a solid suddenly forms. Okay, so use that a little common sense with this definition and don't assume just because something evaporates or melts that you saw an actual chemical change there or a chemical reaction. Okay, so now we also need to look at some of the symbols that we're going to use when we discuss chemical reactions. So the first symbol that we'll use, you're probably familiar with, is just a reaction arrow. Okay, so we put the reactants on this side, we put the products on this side, the arrow just shows us a reaction happen. Okay. So if you see this symbol, okay, that means a reaction didn't happen. Okay, that means we tried to put the products over here, we tried to put the reactants over here. We thought these products would be made, but an X over the arrow shows us that a reaction did not happen. Okay, so this type of arrow, you see a double arrow, an arrow pointing in both directions. That means you have a reversible reaction. Okay, so you have reactants over here, products over here, but the reaction could also go in the opposite direction, so the products can be converted back into reactants. And so the next four we're going to look at are very, very important from this point forward. From this point forward in the class, whenever we describe a compound, we will typically have to include one of these four symbols. So we call these the phase symbols. Okay. So the first three are pretty intuitive, and the last one's probably new to you. So the first will have a subscript S. So I'll just show how these look when you write them beside a compound. So H2O subscript S, and you always put these in parentheses, okay? So H2O subscript S means solid water, okay? So that would be ice there. So then we have H2O, we could have a subscript L, okay? I tend to write it as a cursive L. If you want to write a lowercase l, that's fine. Just to be sure it's in parentheses so you know that it's an L and not a 1. That just means liquid water, okay? So the L corresponds to liquid. And then we could have H2O G, okay? So the lowercase g in parentheses just tells me that the compound I'm discussing is a gas. So solid, liquid, and gas are phases we're probably used to. The one new phase symbol that we have, though, is the symbol AQ. Okay? So AQ stands for aqueous. So AQUEOUS. Okay? So AQ refers to an aqueous solution. So I'll go ahead and write aqueous solution. Okay? So what this means is that the compound is dissolved in water. So we can have NaCl solid. Okay, that's the table salt you get out of your salt shaker at home. With the S is when it is the crystalline solid. Then if you dissolve NaCl in water, you have the AQ symbol. Okay, let's think about the difference in AQ aqueous versus L liquid. Okay, so let's just think about iron, for example. Okay. So I could have Fe solid. Okay. So if I heat up that iron, it's going to melt. Okay. So I apply some heat and I melt iron. So now I have liquid iron. So we'll just say heat. I had to melt it to get there. But let's say you take the solid iron, you mix it with water, and it dissolves. Okay. Then you have aqueous iron. So the difference in this and this other than how we got there from the original solid iron, this would be pure iron still. It would just be melted iron. It would be iron in the liquid form. This would no longer be pure iron. It is iron atoms that have been broken apart in a solution of water. Okay. So anytime you see the symbol AQ, you have to be aware whatever I have is present in a solution of water. Okay, so we'll discuss that in great detail when we look at the solubility rules for double replacement reactions. Okay, so just keep in mind, any reaction we do from this point forward, don't forget to think about if we need phase symbols. As we go through the reactions, I'll tell you when we need them and for what types of reactions we'll need them. And then be sure you keep straight in your mind aqueous versus liquid here. Okay, so the next two symbols that we'll use is a vertical arrow, either pointing up or pointing down. So if I have, we'll just say 2 and an arrow going up, okay, that means that oxygen gas was produced. Okay, so if you produce gas in a liquid, where is it going to go? Yeah, it's going to bubble up to the top. So the other option would be something like this. That would be a downward arrow. Okay, so a downward arrow means that we have a solid produced. So if you have a liquid doing a chemical reaction and you produce a solid, where is it likely going to go? Yeah, it's going to go down to the bottom of the container. So be aware of these symbols. I don't like using them though. Typically if we have a gas produced, we will use the phase symbol, lowercase g. If we have a solid produced, we will use the phase symbol, lowercase s. So I just want to show them to you here to make you aware of them if you see them, but we really won't use these in this class. So the next symbol is very important. You will have a reaction arrow with a triangle over it. Okay, so the triangle means a couple of different things. If you have a triangle before you have a symbol like T, so that's the Greek letter delta, so delta T is change in temperature. Okay, that's not what I mean here. So a triangle above a reaction arrow means heat. Okay, so if I have A, okay, whatever molecule A is, and I want to change it to molecule B, but I write it like this, that means I had to apply some kind of heat. Okay, this is just the generic symbol for that. We don't know how much, but we know some heat was applied. We can also see it written like this. You can see 100 degrees Celsius. Then we know exactly how much heat was applied. And we can see some other things written over the reaction arrow. We can see 2 atm. Okay, so atm, or atmospheres, is a unit of pressure. Okay, so if you see a unit of pressure written above the reaction arrow, that means you applied some type of pressure to the chemical reaction. Or if you see something like KMnO4, potassium permanganate, written above the reaction arrow, anytime there's a chemical above the reaction arrow, that simply means that was a catalyst for the reaction. Okay, so some kind of molecule aided in the chemical reaction process. Okay, so those are the basic symbols that we'll use when talking about chemical reactions. A couple of other things we want to be sure we're familiar with and remember before we dive into the reactions. The first thing, is the diatomic atoms, or the diatomic elements. Okay, so we remember if an element is diatomic, we never see it by itself. We always see it bonded with itself. So if we have hydrogen as our first one, we see it as H2. Nitrogen, we see N2. Oxygen, we see O2. F, we see F2. Cl, we see Cl2. Br, we see Br2. I, we see I2. Remember there's 7 of them. 1, 2, 3, 4, 5, 6, 7. So I got them all. And the last 6 form the number 7 on the periodic table. Okay, so that is a good way to remember that. So I know we've talked about this, but I haven't really shown you an example of where this comes up. So let's think about where this might be observed. So let's just say I have written out in words, iron reacts with oxygen. Okay. So I could write Fe plus O, but because oxygen is one of the special diatomics, it's always going to be O2 there. Or if I had iron reacts with chlorine, then I would have Fe plus Cl2. Okay? So what if I said solid iron reacts with oxygen gas? I would take it one step further, and I would have solid iron plus O2 gas, and then we'll learn how to predict the reaction products later. Okay? So just be aware, anytime you deal with one of these elements by themselves, you will see the subscript 2 there, meaning they're bonded to themselves. And hopefully you remember what these look like, okay, from the previous chapter. So nitrogen bonded to itself looks like this. Oxygen bonded to itself would look like that. And then the halogens just form a single bond between themselves. So you remember that from drawing the Lewis structures. So please don't confuse this with these atoms being in a molecule. So it is perfectly okay to have NaCl, okay, and chlorine. There will only be one chlorine. Okay, the diatomic rule, remember, only applies to when the atom is by itself. Okay, so now let's think about a couple of other things we need to remember before we dive into the reactions. The naming rules for ionic compounds is very, very important. So I think at this point you're probably pretty comfortable naming ionic compounds. If you need a quick refresher, go back to chapter 6, I believe it was, and review the video and review the rules for naming ionic compounds, because they will be very important for this chapter. Okay, so now after getting kind of some background information out of the way, some review information out of the way, once you're comfortable with everything we discussed, all these symbols, all the notations, make sure you remember how to balance the reactions here. We don't want that to hold us up when we're at the chemical equations. I think we're now ready to go ahead and jump in and look at the 5 basic types of chemical reactions that we're going to discuss in this class.